Okay, so today we continue and then finalize this chapter eventually. So the lesson is finished, but I found some interesting problems in Mathematics 5000 book, so I want to share it with you. So more on polynomial equations again. Okay. So as I told you that the lesson is finished, there is no new lesson added, but might be some problems I found in other books, Mathematics 5000, so some of you were following that book, but I saw that there are some interesting problems related to our chapter of this, so I try to write them down to solve and discuss it with you, okay? I start with an example. I just took it from that book, Mathematics 5000, volume 4, and then to see what is going on. Okay, let me just write it down for you. So, example, consider the polynomial instead of p of x, because I am working in complex numbers, so let me write p of z. P of z is equal to z to the 4 plus 2z cubed, and then plus 3z squared, and then plus 2z plus 2. Okay, and this is a given polynomial. This is an interesting question, I would say. Number one, show that I is a root of this polynomial. Okay, number two, solve this equation. Solve p of z equals to 0. So this is what we want to solve today. Okay, so first of all, I hope that you see there is a little bit difference from what we have discussed so far, because I have given you a polynomial. It doesn't matter if I call it x or z in this case. What matters is that I am proposing a root for this equation which is already a complex number. But there is no difference actually. You can do the same thing as you did before. Do you remember? I gave you a polynomial, okay? And if I ask you to solve it, by the way, if I don't give this piece of information, do you remember what I told you before? You only can hope that the roots are integer, and if that is the case, they are among the divisors of that number. So plus or minus 2, plus or minus 1. Assume that I haven't given you this piece of information, so you take plus or minus 1, plus or minus 2, and check it here. For plus signs, there is no hope because all of them are positive, so it is clear that if I put 1 or 2, it does not become 0. What about minus 1? If I put minus 1 here, it becomes 1 minus 2 plus 3 and minus 2 plus 2, which is not 0. If I put minus 2 there, let me just do this in a scratch work. So if I put minus 2 here, it becomes 16. This becomes minus 16. This becomes 12. This becomes minus 4 plus 2. But this is not 0, yes? So it means that unfortunately we have to give up because we don't know what to do anymore. But the good news is that they have also provided us with a guide for us here. So you see, the only thing that I could do if I didn't see this guide is to hope that there is an integer root for this and then where to look for among the divisors of that one. But when I check them, unfortunately none of them work, so it means that I don't have anything to do anymore, unless I am so creative that I can factorize it on top of my head, which is not that easy. Okay, especially in this case, you will see it is not easy at all. But now we want to solve the problem. They have provided us with somehow a guide. It's also a part of the problem, but a very, very easy part. The main goal is not giving you a simple question. The main thing is that giving you this as a guide for the second part. Okay, so let us now check if it is true or false. The first one is easy. So what I have to do, number one, I have to replace z with I to see if the answer is indeed 0. So I put I here, so this becomes I to power 4 plus 2I to power 3 plus 3I to power 2 plus 2 times I plus 2. And let us simplify this. I to power 4, what is I to power 4? I to power 4 means I to power 2 to the power of 2 again. But I to power 2 is negative 1, so negative 1 to power 2 is just simply 1. So I to power 4 is 1. I to power 3 means I to power 2 times I. But I to power 2 is minus 1, so it becomes minus I. So instead of I3, I put minus I, it becomes minus 2I. And then I go here, I squared is negative 1, so it becomes negative 3. 2I is just 2I, I cannot do anything with that. And then I have 2 here. But you see now, minus 2I and 2I are cancelled. 1 plus 2 is 3, minus 3 is 0. So that is correct. So when I replaced z with I got 0. So it means that, therefore, I is a root. Okay, so now I want to start a solution that I want you to feel that, because it's better to see that this does not work that easily. Okay, but at least I expect you to be able to tell me what to do now. Now that I know that I is a root, I can somehow factorize it, but using the long division method. But the long division method so far we haven't used for complex numbers, but this time we want to use it for complex numbers. But I want you to be patient and see, even if I succeed to do that, then still my problem is not solved. Why is that? You will see. I think you should be able to predict as well, but let us see. I will take this one, z to the 4 plus, this is a little bit tricky, so you need to pay attention to learn. So this one plus 3z squared, and then plus 2z. So I intentionally write it a little bit big so that I have enough space, and then I divide it. But this I expect you to tell me. Divide by what? The first one confirms, the first step confirms that I is a root. So this means that this polynomial is divisible by... Any answers? Say something, yes. It should be divisible by, so when you say it is divisible, this is not something that you need to push hard on your memory. The places that you need to push hard on your memory, you don't actually do that. But whenever you push your, so you shouldn't remember something. This is divisible by, so the root is, so I is a root of this. What does it mean? It means that when you factorize this, you see some pair of brackets, apparently, I don't know how many, but you know that when I put I here somewhere, the answer should be 0. So you can say that at least one of them is what? Z minus I, yes? I don't know what happens for the next, but one of them should be Z minus I. So this means that this is divisible by what? Z minus I. But this becomes rather technical because you have to be careful about how you treat imaginary numbers. This is the first time that we are doing the long division for complex numbers. Okay? So what you do, you take the first one and the first one here, you divide this one by that one, it becomes z to power 3, and you write it up there. And then you multiply, as before, you multiply this by the whole expression here, and write them here with the opposite signs. So z3 times z is z4, but when I want to move it here, I write minus z to the 4. z3 times negative I becomes negative I z3, but I change its sign when I want to move it here, so it becomes positive I z3. Okay? So the reason that this becomes harder is now clear, because now when I add this one and that one are gone, but this is an I, so if it was just 1 or 3 or whatever, I just add the numbers. But here, this is 2, this is I. Still, I add the numbers, but it cannot be simplified more than that. So 2 and I should be added, and then z to the power of 3. The rest of it I just bring down, yes? And because of this that happens here, this becomes a little bit lengthy. You have to be careful in the calculations. But the procedure is the same. So you take the first term, okay, and then divide it in your head or in the scratch paper by that first term, which is z. If I divide this by z, 1z cancel 1z here, 2 z's are left, and 2 plus I is also left. So I would write plus 2 plus I z squared. Then what I have to do, I have to multiply this expression by everything here, put them with opposite signs here. So this one, multiplied by the first one, becomes plus 2 plus I times z cubed, but I myself have to change the sign. Okay, and then I multiply this by that, it becomes negative I times 2 plus I times z squared, but I told you, you have to change the sign. And then I do this addition, this one added to this one, they are totally gone. But this one and this one, I factor a z squared out, yes? And then I times 2 plus I, so which becomes 2I plus I squared, which is minus 1, and then plus 3. Yes? And instead of minus 1 plus 3, if you don't mind, let me just write plus 2. Yes? Yes, so what I did, I just added this one to that one. So if you want, I can write here for you. So I factored a z squared out. I times 2 plus I from here, plus 3. And I multiplied this in, and I simplified, I got that. But there are 2 more terms left over, so I just bring them down. And I just continue the process. Okay, so what should I do? Again, I take the first term, and the first term here, and then divide this. So it becomes plus 2i plus 2z. I multiply it by the whole expression and write it here by the opposite sign. This one multiplied by minus I is minus I times 2i plus 1, plus 2, but times z, but I have to change the sign. And then one more. Hopefully I haven't done any mistakes. So this is gone with that one. But then this is z, this is 2z. I factor a z out and then add these two. Yes, so I can do the scratch work here. So I have a 2 here. And I have I times this expression. So it becomes 2i squared plus 2i. But 2i squared is negative 2, which cancel this positive 2, and 2i is left. So when I add this one to that one, there is only 2i left. And then there is a z, and there is also a 2 that I have to bring down. And there is only one more step left, and I think we are done. Yes. So I take this 2iz and I divide it by z, it becomes 2I. And I multiply 2I, it becomes 2iz. I change the sign. Let us do it in our head. 2I times negative I becomes negative 2I squared. Negative 2I squared is positive 2. But when I bring it down, I have to change the sign. So everything is good. This one and that one, this one and that one are gone. And as I expected, the remainder becomes 0. So this is exactly the thing that we did before, but it's a little bit more tedious here. But still, it doesn't help. Can you see why? Let us see. What can I write? I can write that, okay, P of z is this expression multiplied by that expression plus the remainder, but the remainder is 0. So I just write z minus I times that expression. Z to power 3 plus 2 plus I z squared. If you want, you can also factor a 2 out. It doesn't matter that much. But let me just write it as it is. 2I plus 2, and then I have z, then I have plus 2I. And the whole expression. So I was able to factorize it. But this factorization, I would say, it is not that helpful. Yes? Why this is factorized? First of all, I want you to see that your prediction was correct, yes? Z minus I appears. But in my case, only one pair of brackets appeared. But anyway, Z minus I is there, and there is another expression here. They multiply to each other. If you don't believe, you have to be patient and multiply this back, and you will see that you will get this result. But why do you think it is not that useful here now? Because you know that the reason that I do this, because I want to solve the equation. Okay? So if I want to solve the equation, it means that I would P of z equals to 0. This means that this expression is 0. So z to power 3, sorry. And then z squared plus 2I plus 2 times z plus 2I. This is equal to 0. That is correct. But why do you think it is not that useful? There is a simple answer to this, because you cannot solve it, yes? Why is that? Because you say that the zero product rule tells me that either the first one is 0, which is not a good, this is not a very nice thing to, because we already knew that, so that's not something new. Z equals to I is a root, but either this one is 0, which does not give rise to any new information, or this one is 0. This one is 0 is still hard, yes, because of course this in principle should be easier. To be honest, not that easier, even though this is a 4th degree polynomial, but at least you didn't have complex coefficients. Here I have a 3rd degree polynomial that should be in principle simpler to solve, but the price that I am paying for that is at least I am having the complex numbers as coefficients. So I wouldn't say it is easier to solve. Is that clear? So at least the reason that I brought this up, because I want you to learn, there are some exercises in your book that you are supposed to do the long division by complex numbers. So that is an example for those cases. Another thing that I want to teach you a theorem which is actually also in your book, and it is very helpful for this case. Okay. Any questions here? So I just want you to understand the method that we used before, we just used here, but it was not that effective, because still we don't know how to solve the problem. But there is a very nice theorem that I want to go through it today, and then use that theorem to again come back to this problem. That theorem is this. So let me write theorem. This theorem is good to remember, okay? So, let P of z be a polynomial with real coefficients This is extremely important. Real coefficients. If Z node is, if the complex number Z node, let me write it like this. If the complex number Z node is a root of this polynomial, then Z node bar, the complex conjugate, then Z node bar is also a root of this polynomial. Okay, so, but this is not for all type of polynomials, but for polynomials whose coefficients are real, are all real. For example, this rule works for this polynomial because the coefficients are 1, 2, 3, 2, and 2, which are real, but this rule does not apply to this part because this is a polynomial, but the coefficients are not all real. Okay? So if I want to summarize this, this tells you that P, a polynomial with real coefficients, okay, and we also know that P of Z node is equal to 0. This tells you that if you want to, you can conclude that P of Z node bar is also 0. So this is the summary of what you see in words here. Okay, first of all, let us see why this idea is correct in the first place. Okay, it's very simple to understand. Okay, so I would say that if I want to prove it for you, I would say let P of x be a polynomial of, say, degree n, but with real coefficients. So an z to power n plus an minus 1 z to power n minus 1, continue until 1 z to power 1 plus a node. Okay, so let this, oh sorry, this is not px, p of z. Okay, so what we know about this polynomial, I know that these numbers that you see, an minus 1, a1, a0 are real. This is mentioned, the real coefficients are all real. And we know something more. We know that P of Z node is 0. We want to show that P of Z node bar is also 0. But that is very easy, you see, because you tell me that P of Z node is 0. From this, I can conclude this, that if I go to my polynomial, replace Z with Z node everywhere, the result is 0. That is the meaning of P of Z node be 0, okay? So this means that an Z node n plus a sub n minus 1 Z node n minus 1 plus a1 Z node plus a node is equal to 0. That is the meaning, yes? If you have a polynomial and you tell me that Z node is a root of that equation, it means that if you replace the variable of the equation with the proposed number, the answer becomes 0. That is the meaning of being a root, yes? But now you are telling me that this number is 0. So it means that the complex conjugate of this is equal to the complex conjugate of that. If two numbers are equal, the complex conjugates are also equal. There is nothing to do on the right hand side. What is the complex conjugate of 0? It is 0 itself. But do you remember we had this theorem before? If I have the sum of some complex numbers and I want to find the conjugate, I can break it into parts, yes? So I can write the conjugate of the first one plus the conjugate of the second one plus up to conjugate of this one, and finally the conjugate of the last one. Yes? Okay, now, for example, can you tell me what can I write instead of the last term? I can write it simpler. Why? So I copy and paste this one. So what is the complex conjugate of a node? So you have to respect this condition. A polynomial with real coefficients. So it means that a node is a real number. If it's a real number, its conjugate is it's equal to itself. So I can replace it safely with a node itself. But for the time being, let us keep it. I want to remove all of them if possible in one place, okay? But let us come back here. It's a product. We learned that the conjugate of the product is the conjugate of the first one multiplied by the conjugate of the second one. Plus the same thing here. Conjugate of the first one multiplied by conjugate of the second one. And then you continue this process. This one, conjugate the first one, conjugate the second one, and then at the end this one. Now, hopefully you know, instead of an bar, I can write an, because an is real, as you just mentioned. But here, do you remember we also had this rule that if I have z to power n, then conjugate, if I want to raise first to power n, then conjugate, it becomes equal to if I conjugate first and then raise to power. So I want to use this rule. So this one can be written as z node conjugate, then to power n. This one, I just remove it because it is real. And this one, I make the conjugate first and then raise it to power n. And then I continue. Here, this is just a1. This I cannot do anything with it, just copy and paste. And then I would write a node at the end is equal to 0. Yes? Now what is happening? If I ask you, can you write something very compact for this one? You would say yes. Because if I compare this one with my polynomial, you see that they are more or less identical. The only difference is that every appearance of z is replaced by z node bar. So this means that this expression is nothing except b of z node bar. And on the right hand side you have 0. So this is the end of the proof, yes? I started from knowing that p of z node is 0. I was able to show that, okay, in that case, p of z node bar is also 0. Okay? But be careful, this theorem is only true if my coefficients are all real. Okay, but can you tell me how this theorem will help me to solve that problem easier? Because this proof is not important for this problem, I want to erase this one, but let me just see what is going on here. So here, I want to come back to the problem, and I want to solve this problem once more. Of course, I was not succeeded to solve it completely, but I want to use this theorem somehow to be able to do that completely. Okay, but let me clean the theorem here, and I ask for your opinion about it. Do you have any opinion how this theorem is useful for solving that problem? Okay, let me guide you a little by little, okay? So, first of all, tell me, is it a good type? Is it a polynomial of the type for this theorem? Yes, because I have a polynomial. All the coefficients are real. So, and then I know something else. I know that I is a root of this polynomial. Okay, so I would say that the coefficients, so I go back to the problem again. The coefficients of P are all real. On the other hand, in this step, I realize that I is a root. So I realize that P of I is 0. But can you tell me how can I use this theorem? I can say I immediately know another root. This tells you that if you know a complex root for this polynomial, the next one is its conjugate. At least one more you know. Okay? So P of I is 0. Can you tell me what can I conclude using this theorem? Yes?
P of minus 1 minus I
is equal to 0. Yes? So this implies that P of I conjugate is 0, which, as Nabila mentioned, this is P of minus I equals to 0. Now let us see how this will help to solve the problem that I couldn't solve before. Because when you say P of I is 0, now I know something more. You see, I told you that if I ask you to factorize this, I don't know how many pair of brackets I will face, but I know that Z minus I is one of them. I now know one thing more, which I didn't know before. This is extremely important to understand. In this way of solving, that was the only piece of information for me. I couldn't predict what is happening for the next pair of brackets. But this tells me that Z minus I is somewhere there, definitely, as we had before. But now I have some extra piece of information. Can you predict what this one is, definitely? Now you know that minus I is also a root. So what should be here?
Z plus I.
Yeah, Z plus I, thank you. So Z plus I, but do I know something here? Not yet. I don't know. Is that clear or not? Because P of minus I is 0, so it means that there should be a factor so that when you replace Z with minus I, it turns to be 0, yes? Because of the 0 product rule. We already knew that Z minus I is there because I had this piece of information. Now, because of that theorem, I am now sure that minus I is also a root, so it means Z plus I should also appear, which I didn't see this before in my solution. Yes or no? Okay. But if you ask me what this is, I don't know. But we can immediately find that. But one thing I am sure. Can you tell me what is the degree of this leftover? The degree of the original one is 4. In this case, I factorized that to a degree 1 and a degree 3. This problem was hard because I couldn't solve degree 3 either. But now, can you tell me what is the degree of this leftover, at least? 2, yes? Because this is degree 4. This is degree 1 times degree 1. This is already degree 2. So there should be degree 2. And then I am sure that there is no problem left for me. Because definitely, if you are in math 4, of course, you should be able to solve a second degree equation, yes? So this means that my problem is solved. But now, instead of dividing, then you might say that, okay, should I divide once by this, once by that? No. You see that this is very tedious and it is not helpful if you want to separately divide. The point is to multiply them. So to write P of Z is equal to, what is the multiplication? It's a conjugate rule. It becomes Z squared minus I squared. And then this question mark is still left. But there is a better name for I squared. It is minus 1, so it becomes positive 1. Now everything is clear. Instead of dividing by Z minus I, which I ran into problems, I divide by Z squared plus 1. And this explanation guarantees that the remainder will again be 0. Don't worry about the remainder, because we realize that. Okay, now hopefully we can finally solve the problem. Yes, so let us see. This long division is also simpler than the previous one because it doesn't include any complex numbers at all. So it goes very smoothly in lower steps. Okay, so what I do, let us practice again. The people actually, for Math 4, it is important to be able to do this long division, so that at least the people who are not interested at these high-level questions, they can listen to learn how to divide. Okay, z to the power of 4 plus 2z cubed, and then plus 3z squared, and then plus 2z plus 2. I want to divide this by z squared plus 1. I just want you to learn the logic. Of course, doing these mathematical calculations are also interesting, but the main point is to understand why this method is working. Okay, so now let us do that. I take the first one, divide by the first one, it becomes z squared. I write it down, I multiply it there, and then change the sign and put them here. So it becomes minus z4, and z squared becomes minus z squared. But be careful here, this one and that one are gone. This is not addable to this one, because this is 3, this is 2. This is addable to this one. But you have to respect the order, so you have to bring this down first. And minus z squared plus 3z squared is 2z squared, and then the leftovers are 2z and 2. And I repeat the process. 2z cubed divided by z squared is just simply 2z. Multiply it there back and write it with different signs. So it becomes what? Minus 2z cubed minus 2z. Again, the same story, so don't be careful. This one is similar to that one. This one with that one are gone. I bring this down, and then 2. And then finally, I divide the first term by the first term. It becomes 2. Multiply it here, change the sign. Finally, I am done. It becomes. Okay? So now this question mark that was not clear for us, now it becomes clear. That question mark is this expression. Yes? So this question mark. So now I clean it, and I write z squared plus 2z plus 2. Yes? And now my goal was to solve the equation. The problem is solved actually. This one goes to z, this becomes 0 if z plus 1 is 0, or this one is 0. But I don't need to bother to solve the first one because there is nothing new for me. I already knew I and minus I are the answers, so there is no surprise if I get them back. So forget about it. So if you want, you can write z is equal to plus or minus I. But this one I have to solve. But there's no problem for solving this, yes, hopefully. So z is minus 2 plus or minus the square root of this number to power 2 minus 4 times a times c divided by 2 times a. And the answer becomes what? Minus 2. This is minus 4, so it becomes plus or minus. 4 becomes 2, negative 1 becomes I. And then divided by 2. So you see that you got the answers finally. So it is minus 1 plus or minus I. So if I ask you how many roots we have for this polynomial, we have 4 roots, and all of them are complex numbers. Even not single one of them is a real number. So this is what I saw in this Matematik 5000 book. I got it interesting. So, and then you also have it in your own book, something like that. But I will solve one more example from Matematik 5000, and then the lesson for this chapter is totally finished. As I told you that next week, or probably, no, this week there's a Friday, I will teach a little bit what I skipped, and that was the application of integrals in probability theory. So that one will be a question in the national exam. So I will teach that one, and then the next week you will get time to practice. I think it would be better to practice together on a national exam questions from the beginning to the end to see how it goes. Okay? Okay, let me write a final example for this chapter. It was a very long technical chapter, but it's good that we were able to finish it on time. Okay. So this is the question. It has nothing to do with theorems or something like that. The method of proof might be somehow useful, but there is no new information there for this problem. The example is this. the equation z to the power of 4 plus 6z cubed plus 13z squared plus 18z plus 30 equals to 0 has a pure imaginary root. Solve the equation. Okay, so I think it would be good if you can think a little bit 5 minutes for yourself about it. So there is a very big equation of fourth degree. We even don't know the root, but we know something. We know that there is one root at least for this equation, which is pure imaginary. It means the real part of that complex number is 0. Based on this piece of information, they are expecting us to be able to solve this equation. Okay? Okay, any ideas? I don't know myself. Let me see if I can solve it. Yes, here, let us use this. The equation is guaranteed to have a pure imaginary root. So I would say that, for example, let W be the pure imaginary root of this equation whose existence is guaranteed, yes? How do you write guaranteed? I think it's right, is it? Anyway, whose existence is guaranteed by the problem. Okay, what does it mean? First of all, what can I say about W? Because it is pure imaginary, let me put in prayer brackets, might be I need that. I know that W bar is what? Is what if it is pure imaginary? No, the real part is 0. So the imaginary, so this one becomes what? No, it is not W. So pure imaginary means, for example, 2i. There are no real parts, only imaginary parts. So W bar is minus 2i. It is minus W. Yes? When you say it's a pure imaginary number, it means that its conjugate is negative of itself. Okay, but on the other hand, by the way, I don't know the solution, so I'm just thinking loudly, okay? So what happens is that, what I know is that this W satisfies the equation because it is claimed to be a root, yes? So W is a root. This means that it satisfies my equation. So W to the power of 4 plus 6Z W to power 3 plus 13 W to power 2 plus 18 W plus 30 is equal to 0, okay? Because the only piece of information that I have is this, so it motivates you to do something. What's the motivation? I mean, it is natural, still I don't know what's going on, but I have some ideas. So W bar is minus W, and that is the only piece of information provided for us. If I want to use it somehow, what should I do? Take the conjugate, yes? If this is true, I take the conjugate here and the conjugate there, yes? So you will see why. I have some ideas, but not quite. I don't know exactly what is going on. I don't need to make sure that what is going on exactly. But this one bar becomes the 0 bar. Okay? But let me don't repeat these things. So you see this bar can be decomposed into bars, and then it goes to W's, yes? So this becomes W4 bar, but I can interchange them so it becomes W bar 4. And then for the same reason, this becomes 6W bar 3, 13W bar 2, plus 18W bar. Of course, I have to take 18 bar W bar, but 18 bar is 18. And this 30 bar is just 30, 0. Yes? But now, because of this thing, W bar is pure W is pure imaginary, so W bar and minus W are the same. So it means that I can take everything that I see here and replace it with minus W. It might help, I don't know, I'm just thinking loudly as I told you. So this becomes minus W to power 4. This becomes what? 6 plus 6 minus W to power 3 plus 13 minus W to power 2 plus 18 times minus W and then plus 30 equals to 0. Yes, understandable? But then this one goes to power 4. It is good. I can get rid of this minus sign, but you see that the next one becomes negative. That was the way I just thought up to here, and I'm hoping that I could do it. I could do the rest. So this becomes W to power 4. This one becomes minus 6W to power 3. This one becomes positive 13W squared. And then this one becomes minus 18W. And then plus 30 equals to 0. So what I get, I already knew this from the beginning. Still, if you tell me, do you know W, I would say no. I just know that this is pure imaginary. But I also realize that this is also true for that particular W. Okay. So I was hoping that I can continue somehow after that. Do you have any idea what to do now? Any ideas? Any ideas at all? You should have some ideas, yes? You see, if you tell me, do I know W, I would say no. But for that hypothetical W, I know two relations. One, this one, another one, this one. So how can I use these pieces of information to narrow down where W can be, yes?
You put the two equations equal to each other?
That is good, but that is not my intention. Not equal to each other, but because you are right. You are telling me somehow, no, you are right. You are right. Okay, I will do that. But my intention was to multiply this by a negative sign and add them. Yes, that's also true, because you say this is 0, this is 0, they have to be equal. So let us follow yours, okay? So this becomes W4 plus 6W3 plus 13W squared plus 18W plus 30 is equal to 0. This one is also 0, so they have to be equal themselves, yes? Okay, but you see that many things will be simplified now, yes? Because I move W4 to the left, this will be cancelled. I move 30 to the left, this will be cancelled. Is there anything more? Yes. 13y squared moved to the left, this will be cancelled. But when I move this to the left, it becomes positive 6, another positive 6, it becomes 12W3. Yes? And then what is left again? 18W plus 18W is 36W equals to 0. I divide everything by 12. So this becomes W to the power of 3 plus 3W. It's equal to 0. Yes? And then at least I can solve this equation. Even though it is a third degree, I don't even need long division because factorization is very simple now. So w, and then I have w squared plus 3. Okay? And then I put this one equal to 0. Then I get 3 solutions, yes? One solution is w equals to 0. And then when I put this one equal to 0, then I take the square root, it becomes plus or minus the square root of minus 3, but this can be written as a square root of 3i. So this means that one answer is the square root of 3i, and the other answer is minus a square root of 3i. Yes? So which one of them is acceptable?
Square root of 3i.
Yes. Both of them are acceptable, but not this one. Because first of all, w is a real number, not a pure imaginary number. On the other hand, w is a false root because you see, if you put 0 here, it doesn't work. It becomes 0 plus 30. So w equals to 0 is not there. But you also could predict this will happen. Could you predict that these roots come in pairs? They are conjugate pairs of each other. That is clear because I told you that if you have a polynomial equation with real coefficients, if there is a root for that equation, the conjugate is also a root. Yes? So that is easy to see. Okay. Okay, now the problem is that how can I solve the original equation now? So the number that was claimed by the problem, we were able to find it. We were able to find it. Two numbers. One of them you can assume that the square root of 3i. The other one minus 3 is minus the square root of 3i. Yes. I'm not sure. Do we need to check that this is also a really root or a fake root? No, that is correct. This is inevitable because we did this before. According to the theorem, there is a pure imaginary number as a root, and then this is inevitable. If this is a root, this also has to be a root. There is no other possibilities. Okay, but I hope that you agree this turns back to the previous problem, yes? Now I have a polynomial of degree 4. Instead of knowing one root of it, I just got two of them. And then I can use the same trick, yes? But I just want to make sure the final step. If I factorize this polynomial, let me call it P of z. P of z should be factorized to a number of terms. But I know that the square root of 3i is a root. So what can I write as one of the factors? This I don't know why you hesitate to say. Did you learn that at the end? So square root of 3 is a root. So what can I say about one of these factors? The square root of 3i. Okay, so this I use this fact. But there is also another root here. So what can I write for the second one? What? Z plus square root of 3i. And this is question. But do you see that's exactly the same problem? And then don't get confused to divide separately. Because now you can combine them. What is the product of them, by the way? It is the first one squared minus the second one squared. But the second one squared is just 3i squared. Sorry, yes, 3i squared, which is negative 3. But there is also a negative sign here, so it's positive 3. And then this question one. Yes? So if we have done everything right, by what they gave to us, we realize that this polynomial, in a very indirect way, we realize that this polynomial should be divisible by that. Yes? So then it means that we can safely go and divide this polynomial by that expression and hope that we can solve the problem. Yes? Okay, so let me just do it fast so that we make sure that we haven't done any mistakes. So I would say this is the hardest problem I just realized in this Matematik 5000 book. So it's first of all, it shows that this is really at your level, it's A-level question. There, okay? So if you want to solve that problem, so let us just do that. Hopefully we haven't done any mistakes. So this, so I have to divide this by z squared plus 3. So let us just repeat it quickly. So I just divide that by that, z squared I multiply here. And then this becomes this cubed plus 10z squared plus 18z plus 30. And I do this process again, so it becomes 6z. You can also watch my calculations. If I am doing mistakes, please let me know. And then this becomes minus 18, so it becomes positive 18. This is a little bit strange for me. This goes 10z squared plus 36z plus 30, yes? Okay, this is bad. Am I doing something wrong? Because this doesn't fit to the problem, yes. Okay, so once more, let me test. Z squared multiplied by that, that is correct. When I add them, this becomes down, and then this one and that one becomes 10, 18, 30. So that is not wrong. Then I divide this by that, it is 6z multiplied there. It is 18, oh, okay. Okay. I forgot to change the sign here. Yes, that is good now, yes? This one and that one are gone. That was my mistake. So that is, this one and that one are gone. 10z squared plus 30. And then you divide, there is a 10 here. And then it becomes minus 10z squared minus 30. So that's correct. This becomes. I forgot to write this minus. Okay, now because when I wrote it with positive, I realized that the remainder cannot be 0, but that is wrong. We confirmed that the remainder should be 0. So this means that that question mark that you didn't know, now you know. It is this expression. So this means that P of z is equal to z squared plus 3 times this expression. Z squared plus 6z plus 10. And then if you want to solve it, you only need to solve that because the root of this you already know. So you solve that one. So it's minus 6 plus or minus 36 minus 40 divided by 2. So it becomes minus 6 plus or minus 2i divided by 2. So minus 3 plus or minus I. So these are two roots, and these are also two roots of that equation. So I would consider it a really hard problem because the information given was given in a really disguised form. So you have to know a lot of things to be able to solve the problem. But you see that it is not that hard to understand what to do, because when they say pure imaginary, remember it means that you have only this piece of information available. And then when you have only this piece of information, it is natural to take the conjugate because you want to conjugate to a pair. And then you see that Nabila actually told what to do after that. We put that one and then suddenly we found the root. And then immediately it becomes the previous problem. So if you have done your homework before very well, at this point you are relieved, okay? Okay, any questions? No? Okay, thank you very much. Yeah, we stopped the lesson and goodbye. Thank you.